So today we are going to study with a new chapter called Newton's Law of Motion. Okay? So what are these Newton's Law of Motion? So in Newton's Law of Motion we deal with the relationship between force and acceleration. In kinematics, I have often told you that acceleration is the consequence of force. That means acceleration is tending to change the velocity of an object. That means acceleration is changing the velocity of an object. Okay. Now in this chapter we'll discuss how force causes an acceleration. Okay. So one important thing that I have to tell before starting this chapter is your knowledge of vectors should be good. If you haven't seen my videos of vector, go and see them. You need vectors in this chapter. We'll draw a lot of free body diagrams. What are free body diagrams? I'll tell you. We'll learn some technicalities. But I am assuming that you have seen my videos of vectors. Okay. So we'll study with Newton's law of motion. So let's begin. Newton's law of motion. Newton's law of motion. So in this chapter we'll mainly study about few terminologies. Terminology means force, momentum and some free body diagram. What are those? I'll tell you little by little. Okay. After that we'll learn first Newton's first law of motion, then Newton's second law of motion and Newton's third law of motion. And then in the last unit of this chapter we'll study a little bit about friction. Okay. So we'll study about force, momentum, free body diagram, These are nothing but terminologies. Okay, terminologies means they are terms for specific things that I'll explain you later. Then Newton's first law of motion, second law of motion and Newton's third law of motion. Okay, and we'll end the chapter with a little bit of discussion with friction. Not little bit, we'll considerably discuss friction, but we'll discuss friction. Okay. Now, so let's begin with terminologies. Terminologies means terms that are required. Terminologies. Okay. So we'll start with something called inertia. So in your NCERT, inertia is a property of motion or of mass. Inertia is nothing. If you want to summarize the term inertia is nothing but the philosopher's version of mass. What do I mean? Inertia is nothing but philosopher's version of mass. But sir, we already have mass. Why we needed to learn about philosopher's version of mass or inertia? See, inertia was coined by Newton. Okay, and on those journals, things were written very philosophically. Maths wasn't, as advanced as it is now. So instead of unit and dimension, they said that a heavier mass will be more difficult to change its velocity. Suppose I apply 1 Newton to a heavier mass, okay, and 1 Newton to a lighter mass. Inertia says that the term inertia means they specifically coined this term to point out that the lighter mass will change its velocity faster than the heavier mass with same amount of force. Okay, so inertia is nothing but a philosophical or philosopher's version of mass. Okay, and has no units and dimension. No units or dimension. That means mass has a unit, okay, kg, and dimension of m. Philosopher's version of mass, or which is called inertia, has no units or dimension. Okay, it's just an abstract term coined to explain that effect. Okay, now momentum. You have to remember this. Okay, this momentum. Momentum is nothing but a product of mass into velocity. Okay, momentum is nothing but a product of mass into velocity. Now, velocity is a vector quantity and mass is a scalar quantity. So whenever a scalar quantity is multiplied by a vector quantity, we obtain a vector quantity. So we know that momentum is a vector quantity. Vector quantity. So this is the definition of momentum. See, in your books it is written the just under from 11-12. Okay, use the formulas to define something, not the other way around. Okay, do not use definition to arrive at the formula. Use the formula to arrive at the definition. Okay, focus on your mathematical approach more. Okay? Now, force. So what is force? Force is nothing but a push or pull. Suppose I am pushing something. Suppose this is a duster. Okay. Suppose I am pushing something. Okay. So this push or I am pulling something. This pull is called force. Okay. Force is nothing but a push or pull. Okay. Now one more thing you have to remember. To apply force, they necessarily does not have to be in contact. That means I do not have to touch this duster. Not exactly a very good example. You have seen magnet attracts each other. That means if I keep two magnets side by side, they'll tend to move or they're changing its velocity. That means acceleration is happening. If acceleration is happening, force is applied on those bodies. Okay, those are called electromagnetic force. And that means, but the magnets are not touching each other. That means to apply a force, you do not necessarily have to touch the body. Okay, not necessarily has to be in contact for applying force. Not necessary to be a contact force. Okay, force can be applied without contacting the body. Okay, and the last thing we'll learn about is free body diagram. Free body diagram. So right now I'm just giving you the definition of free body diagram. We'll discuss this free body diagram in a in-depth detail a little bit later. Okay, so what is free body diagram? A diagram where the body is isolated from the system and all the forces acting on the body are marked, are drawn. Okay, a diagram where the body is isolated, that means separated, isolated, and all the forces acting on the body, remember this term, acting on the body, is drawn. Okay, acting on the body, not applied by the body. Okay, all the forces that it is receiving. Okay, free body diagram doesn't care about how much forces the body is applying. Okay, it has only taken into consideration the amount of force the body is receiving. Okay, so let's start with definition of Newton's first law of motion. So Newton's first law of motion. So generally I am referring to NCERT for your derivation and for your entire curriculum. So I'll be providing you the exact definition that NCERT has provided you all. So first law, Newton's first law. Okay, every body continues to be in a state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. Okay, so let's write the definition. After that we'll discuss. Every body continues to be in motion. Every body continues to be in its state of rest or of uniform motion in its state of rest or of uniform motion or of uniform motion in a straight line. Okay, in a straight line unless compelled by some external force to act otherwise. Unless compelled by some external force to act otherwise. Okay, so this was from your NCERT. Now what does this law says? This law in simple terms says that a body in motion or body moving with velocity v will continue to move with velocity v unless someone applies an force, or a body with velocity is equals to 0 will be with velocity is equals to 0 unless someone applies force. That means a body does not change its velocity until and unless someone applies any force. That is a simplified version of this. So listen to a story. How did this come? There was a guy named Aristotle. Okay, so he said, if we apply a body in motion, will suppose this duster was moving with velocity. Okay, it will stop after some time. Okay, and heavier body will stop after a longer time, and lighter body will stop after a heavier time. So he said a body will stop with proportional with its mass. Okay, then Newton came in and said, you are not entirely correct. Okay, a body moving with velocity v will continue to move with velocity v. Then Aristotle and him, although they are, one was dead when the other one was born. Okay, so suppose there is a hypothetical argument between the two. See, Aristotle is saying, see my observation, if this duster was moving with some velocity v, it stopped after some time, but according to your law, it should be continue to move with velocity v throughout for eternity. Okay, so Newton said that you are not taking account into the consideration of force that is applied in this body. In Earth, everything is imperfect. That means we have something called friction force. So while moving with velocity, a friction force is acting on the backward direction, which is changing its velocity to 0. Okay, if you go to space and repeat the same experiment, if you throw a duster in space with some velocity, it will continue to move with that velocity for eternity. Okay, so that was what Newton said. Okay, so after that we'll do a question. Physical independence of force is a consequence of option A, third law of motion, second law of motion, first law of motion, all of this. So most of you haven't understood the question only. Okay, the question simply says, which law of Newton can be demonstrated without the use of any term force? Which law of Newton can be demonstrated without using the term force, and it is first law of motion. The first law of motion is nothing but the preservation of velocity, okay, or preservation of moment, what is momentum will come later, but the first law specifically says about preservation of velocity. The velocity will not change until and unless someone applies some force. If velocity is equals to 0, it will remain 0. If velocity is with some velocity v, it will continue to move with velocity v. Okay. So after that, we'll learn something about Newton's second law of motion. Newton's second law of motion. Second law of motion. So the definition of second law of motion, I am strictly copying from NCERT. Okay. So why am I copying in your boards? So this, so it will be helpful for, sometimes they can give you which one of the following option is correct, and specifically in competitive exam they'll keep very similar options. So best you focus on the standard definition as given in NCERT. Okay, though such questions haven't come, but it's not the possibility of such questions coming cannot be eliminated. Okay, so let's discuss about second law of motion as given in your NCERT. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. Let's write the rate of change of momentum. The rate of change of momentum of a body is directly proportional. Of a body is directly proportional to the applied force. To the applied force and takes place in the direction in which the force acts. And takes place in the direction in which the force acts. Okay, this was your NCERT definition. The mathematical term of your NCERT definition would be given by F is directly proportional to dP by dt. Okay, but we want to further discuss it. What does it mean? Okay, in simplified term, this is the mathematical term of this definition. I said in 11-12 you cannot go to the definition from the mathematical formula, not the other way around. That means first you have to know the mathematical formula and write the definition in your own words. Okay, so that kind of approach is more suitable out here. Okay, so what does this formula mean? Newton said that a body is there. A body is there of mass m. Okay, it has some momentum. Momentum means, suppose this body was moving with velocity v, so momentum of this body was mv. Okay, now suppose I apply some force. Force is nothing but a push or pull. The body will accelerate. Newton said nothing about changing of velocity or acceleration. Newton said this momentum will change when the force is applied. Okay, but now you said, before I was saying that the velocity will change. How are they related? Okay, what is happening out here? Newton said that when you apply a force in this direction, the momentum in this direction will change. That means, suppose I am applying positive force, that means momentum will increase in this direction only. Okay, that means momentum was a vector quantity and force was a vector quantity. But what is this relation with velocity? Now let's see. Okay, what Newton essentially said was, from Newton's law, F is directly proportional to dP by dt, or rate of change of momentum. Okay, now in physics, just remember, rate of change of anything just divided by dt. Okay, rate of change of displacement, okay, dx by dt, rate of change of velocity, dv by dt, rate of change of acceleration, da by dt, rate of change of momentum, dp by dt, rate of change of anything, rate of change of charge, not rate of change of charge but rate of flow of, whenever you hear the term rate of change, okay, just apply, just divided by dt blindfolded. Okay, that is a mathematical trick in class 11 and 12. So what Newton said was force is directly proportional to rate of change of momentum. Okay, now by further experiment few people decided that force is equals to dp by dt. So what is the difference between proportionality and equals to? Proportionality means any graph, okay, suppose f and dp by dt. Okay, proportionality means this line is a straight line, f and dp by dt is a straight line. Now this straight line can be out here, okay, it can be even out here. F is equals to dp by dt means this straight line is passing through 0 and the angle between, suppose a graph of force versus dp by dt is drawn. Okay, force versus dp by dt is drawn. F is directly proportional to dp by dt means, suppose, and the plot is made of rate of change of momentum with force. This line can pass through anywhere. Okay, F is equals to dp by dt means this line will pass through origin and the angle between them is 45 degree. That means constant is, or the constant of integration, sorry, constant of proportionality is 1. Okay, so that was your mathematical story which you don't need to remember. But if definition come, what is the definition of, mathematical definition of Newton's second law of motion? F is directly proportional to dp by dt, not this one. Okay, this one we found out by experiment. Okay, now what do we know momentum as? Few minutes earlier I have said the definition of momentum. Momentum was nothing but mass, product of mass into velocity. Okay, now if you go to my kinematics chapter on motion in a plane chapter part 1, I have given you few differentiation and integration formulas. One of them was, suppose we are multiplying two variables and differentiating. It is a mathematical topic. We can write this unit as d m into v by dt can be written as d m into v by dt can be written as, you take the first variable, that means m, and you differentiate the second variable, that means dv by dt, plus you take the second variable which is v, and differentiate the first variable. So this is a mathematical concept. Okay, f is equals to md into m into v by dt, where f is equals to m dv by dt plus v dm by dt. Okay, now there is an important concept out here. Usually for most of your bodies, the mass remains same. That means when you apply a force, it is not changing its mass. The mass of the body remains same. So usually for most bodies, the mass remains same. The mass remains same. If the mass remains same, then can I say dm by dt is equals to 0? That means rate of change of mass with respect to time is equals to 0. Why? dm can be written as final mass minus initial mass by final time minus initial time. If mass is equals to constant, final mass would be equals to initial mass. Therefore, they would get cancelled to form 0. Okay, so dm by dt is equals to 0. Therefore, this term is equals to 0 for most cases, not all cases. Okay, for most cases dm by dt, where the mass is not changing, dm by dt is equals to 0. So can I say force is equals to m dv by dt, where the mass of the body remains constant? Now from the chapter of kinematics, what did we learn? What is dv by dt, or rate of change of velocity? dv by dt is nothing but acceleration. Okay, force is equals to mass into acceleration. Okay, this is how, wait a minute. Okay, this is how we arrive F is equals to mass into acceleration. So Newton never said F is equals to ma or F is equals to dp by dt. Newton just said that F is directly proportional to dp by dt, and we arrived at F is equals to, that means we experimentally find out that k or proportionality constant is equals to 1. Now we know that momentum is equals to mass into velocity. Then we applied some mathematics, okay, and arrived when the mass is constant, F is equals to m dv by dt. And from kinematics we know that dv by dt is nothing but acceleration or change of velocity. So this is how we arrive at the formula force is equals to mass into acceleration. Now we'll study a little bit about something called impulse force. Impulse force. Okay. Now imagine two scenarios. Imagine two scenarios. On the left hand side, I kept a body. Okay. I kept a body. Okay. Now I am a little bit, okay, I believe in effort, okay, more than, okay, so I'm pushing it to move the body. I'm applying some force to this body, okay. So when I'm applying the force, the body is continually, see, I'm changing, this is a body, I was pushing it and continually pushing it. That means the force is changing its velocity, okay. That means I'm continually applying the force, and Newton said that force, okay, or F is equals to rate of change of momentum, dp by dt, okay, but this is equals to force. Now let's take a second case. This was a body. The task was to change the velocity of this object. Okay? Change the velocity of this object. Now what did I do? Instead of applying a gradual force, I just applied the force for a very small time. I became Bruce Lee and applied the force for a very small time. So when I applied the force for a very small time, okay, from velocity is equals to 0, this body changed its velocity to some velocity v is equals to v. But after I withdraw my force, it is no longer changing its velocity. Okay, so the force applied for that very small duration is nothing but impulse. That force applied for very small duration is called impulse. So I just became Bruce Lee and applied a force for a very small time. That is called impulse. In some books that is also called impulse force. Now for impulse force, impulse is given by the definition of, mathematical definition of impulse is F dot dt is equals to impulse. Okay, impulse is given by force applied for a very small time. Okay, now see this formula from Newton's second law of motion. F is equals to dp by dt. Okay, so if F dot dt, if you take the dt to the left hand side, we are left with dp, or rate of change of momentum. Sorry, not rate of change of momentum, the change of momentum. Okay, so what is happening out here? This term is the definition of impulse. and in mathematical problem we use change in momentum or final momentum minus initial momentum to calculate this impulse. Okay, in order to numerically solve problems we use the term dp or final momentum minus initial momentum to solve the problem. See, impulse is equals to f dot dt, which is equals to change in momentum. Okay, now let's understand little bit of impulse by problems, by solving problems. So the first problem is a particle of mass is projected with velocity v, making an angle theta with the horizontal. When the particle lands on level ground, the magnitude of change of its momentum will be. That means a projectile motion is there. Projectile motion is there. So it is making an angle 45 with the horizontal and it's moving like this. And I always taught you that a projectile motion is symmetric in the vertical axis. That means velocity at the initial point while going up, the vertical velocity of the initial point while going up is equals to the same vertical velocity while coming down. Okay, that means if this was moving with velocity v out here, this will be moving with velocity v. Okay, if this is angle 45, then this angle or angle that it makes, this angle is also 45. Okay, or this angle is also 45 because a projectile motion is symmetric in the vertical component. Okay, now the question is asking the magnitude of change of momentum. That means change of momentum is equals to final momentum minus initial momentum. Okay, now momentum is a vector quantity. Okay, so what is the final momentum? Final momentum is in this direction with the magnitude of mass of the object into velocity of the object. Okay, so this is 45. This is the direction of final momentum. Now initial momentum is in this direction. See, the direction of initial momentum is in this direction, but we shift this initial momentum out here. Okay, we shift this initial momentum out here, but see, minus of initial momentum, that means we have to reverse the direction of initial momentum. So let us reverse the direction of initial momentum. And we know that from here, when we shift with the horizontal, this angle is also 45 degree, and the magnitude of initial momentum is also 45, in mass into velocity. So the change in momentum is p final minus p initial vector. So the resultant is a vector starting from the tail of first vector to the head of second vector. Okay, so this is the resultant. Okay, now let's draw this diagram a little bit neatly. This angle with the horizontal was 45, and this angle with the horizontal was 45. So can we say this total angle is 90 degree? This total angle is 90 degree. Okay, the magnitude of this vector was mv. Okay, now see, if we apply a little bit of common sense, this triangle, the hypotenuse will be mv square plus mv square under root, which will give us the value of hypotenuse of this triangle would be mv square. Okay, which will give us the answer of mv root 2. So final momentum minus initial momentum would be our option C. Okay, let's do the next question. A ball of mass 0.15 kg, okay, is dropped from a height of 10 meter, strikes the ground and rebounds to the same height. The magnitude of impulse imparted to the ball is nearly. If you have practiced kinematics enough, you know that. So let us draw the situation. A person standing on a roof, okay, the height of the roof was 10 meter. He dropped a ball, that means initial velocity is equal to 0. So the ball came out here and bounced back and reached to the same position. That means when the ball was out here, the ground imparted some amount of force to change the velocity. It is bouncing back, no? So the ground imparted some amount of force for a very small time to change the velocity in opposite direction. So suppose before striking the ground, the momentum or the velocity was v, therefore the momentum was mv. Okay. So when it bounced back, the question says after bouncing back, it reached the same height. Okay. Now from kinematics, we know that to reach the same height, the velocity with which it dropped, the velocity at out here should be equal to the velocity out here. That means the upward motion should have the same velocity to reach the same height. Okay. You can apply the formula and check it. Okay. I don't want to make it lengthy, that's why I am telling you this. Okay. Now before solving any problem, let's determine the direction. Downward is determined as positive and upward is determined as negative. You can take the opposite also, but make it consistent. Your answer will be same. Okay. Now from the previous slide, impulse was nothing but product of f dt, which we measured by change of momentum. Okay. So f dt, or the force applied by the ground for the very small time, very small interval of bouncing back, is equals to change in momentum or final momentum minus initial momentum. Okay. So dp is equals to final momentum minus initial momentum. Okay. So dp is equals to, what is the final momentum? What is the final momentum? Final momentum is in upward direction, that means negative of mv. Negative of mv minus of, what is the initial momentum? Initial momentum is mv in downward direction, and downward direction is positive. Okay. So a change in velocity is minus 2mv. Okay. And why did we now see? So we obtained our change in momentum is equals to minus 2mv, or our impulse applied by the ground in this short interval of time is equals to minus 2mv. Okay. Now we need to find out the velocity. The mass is given but the velocity is not given. Okay. So from kinematics we know that whenever acceleration is constant, that means acceleration out here is only g, we have to apply the formula v is equals to u plus at, where v is the final velocity, u is the initial velocity. So the final velocity you have to find out. Initial velocity is equals to 0. Why? Because the ball is dropped. Plus at, acceleration is nothing but 10 meter per second, because g is 10 meter per second. 10 into, and I have applied the wrong formula because time is not given in the question. So don't worry, there are only 3 formulas that I can apply. V is equals to u plus at, v square is equals to u square plus 2as, and ac is equals to ut plus half at square. So if the first one didn't try out, let's try with the second formula. V square is equals to u square plus 2as. As is nothing but the displacement traveled by the ball. V square is the final velocity that we have to find out. U square is nothing but initial velocity. Initial velocity is 0. Why? The ball is dropped. Okay. Plus 2a. Acceleration is nothing but g. G is given as 10 into s. S is the displacement of ball from here to here, which is given as 10 meter. Okay. So v square is equals to 200. Okay, v square is equals to 200, or v square is equals to 200, or therefore if v square is equals to 200, v is equals to root 200. Root 200 is nothing but 10 root 2. Okay, 100, you all know how to square root 200. Okay, I'm expecting that much expectation I'll keep. Our dp was nothing but change in momentum, which was impulse, was nothing but minus 2 mv. Okay, on minus 2 into m was given as 0.15 kg. 0.15 kg, and the velocity we obtained as 10 root 2. 10 root 2. Now 15 to the 30. From 2 into 0.15 we can apply that as 3 into 10 into root 2. Okay, sorry, 15 into 2 is equals to 0.15 into 2 is equals to 3. Okay, 0.3. Sorry, our question is 0.3, and 0.3 into 10 is 3 root 2. 3 root 2. Okay, 3 root 2. Okay, now there are two values I asked you to memorize. Root 2 was 1.41, root 3 was 1.73, pi is 22 by 7. In calculation of a area, pi by 4 d square, you have heard, no? Pi by 4 is 0.78, but in competitive exam we'll take pi by 4 as 0.8. Okay, it helps in calculation. Then ln2 is 0.693. Okay, so these values you all have to remember. Okay, so 3 into root 2. 3 into root 2 is nothing but 1.41 into 3. 3 ones are 3, 4 3s are 12, 1, 3 ones are 3, 4, and 4.23. So our change in momentum or impulse applied by the ground in that short interval of time is equals to 4.23. Okay, so our correct option is option number B. So why not minus? They are only asking us the magnitude. Okay, it does not mean, see, when they are asking the question, they already assumed you know the direction of impulse. Okay, impulse is also a vector quantity because dp is itself is a vector quantity. Okay, now let's proceed to the next question. A rigid ball of mass strikes a rigid wall at 60 degree and gets reflected without loss of speed as shown in figure. The value of impulse imparted by the wall on the ball will be, that means the ball is, the direction, the diagram is little bit wrong. Okay, make the diagram like this, you can also do opposite, but it's better you follow me. It's better you follow me. It's better you follow me. Okay, now see, the ball came from here, strike the wall and bounce back out here. Now for striking the wall exerted some force for a very small amount on the ball so that it bounced back out here. The velocity vector is changing from this direction to this direction, no? So change in velocity is always accompanied by some force. In order for the velocity to change, there must be some force applied to it. Otherwise, if no force was applied on this ball, that means the ball would continue moving straight. Okay, now let's see, they are asking us find out the impulse applied by the wall on that ball. Impulse is nothing but force applied for a very small time. Numerically, we'll solve that as dp, or change in momentum. Change in momentum is nothing but final momentum minus initial momentum. Okay. Now let's see the direction of final momentum. Final momentum is this side, making an angle 60 degree. Initial momentum is this side, making an angle 60 degree. Okay, making an angle 60 degree. Okay, but since this is minus of initial momentum, that means we have to reverse the direction. We have to reverse the direction of initial momentum, and the resultant is tail of first vector to the head of second vector. Okay, now if we apply a little bit of geometry, this is a straight line, this is a straight line. Now a straight line has 180 degrees. This is 60, this is 60, we can easily say that this is 60. Okay, now the angle made by out here, made by this vector, made by this vector with the horizontal is 60. How? This is nothing but 30 degree. If we draw a straight line from here, this will make 90 degree, and the sum of angles of a triangle is 180 degree. So 30, 90, and the remaining is 60. So this vector will also be 60 degree. So consequently means by natural logic, this will also be 60 degree. Now whenever three angles in a triangle are 60 degree, their sides are also equal. That means if this side has a magnitude of mv, then all sides will have a magnitude of mv. That means P final or final momentum minus initial momentum is mv in the opposite direction, in this direction. But impulse applied by the wall is in this direction, of magnitude is equals to mv. Okay, make a note. You all already know this note, but still make it. A triangle where all the angles are 60 degrees are called equilateral triangle. And in equilateral triangle, all angles are 60 degree and all sides are same. All angles are 60 degree and all sides are same. Okay, this was supposed to learn in your earlier curriculum, but nonetheless. Okay, now out here in the next question we'll solve this exact same question. That's why it is little bit zoomed out, but we'll apply a new method, and this method is more commonly used. Okay, more common method. Okay, so in vectors I taught you how to add there are three ways in which you can add a vector: tail configuration, head-tail configuration, and divide them into vertical and horizontal component, divide them into components and add them. Okay, so in this method, or the most common method in your entire curriculum you'll use is breaking the vector into components, okay, and adding them. This is the most common method we'll use in your curriculum. Okay, break the momentum vector into x and y component, into x and y component, and add them. Okay, now up till now we have already established was impulse is nothing but rate of change of momentum. Sorry, not rate of change of momentum, only change of momentum. Impulse is nothing but only change of momentum. That means dp if someone asks what is the value of impulse, just find out the value of change of momentum, or final momentum minus initial momentum. Okay, now change of momentum is the component of final momentum in x-axis is given by final momentum in x-axis, pfi. That means the component of, see, this ball was going down and this ball was coming out like this and going like this. The component of velocity, if we slap this vector onto this axis, then mv cos theta is the momentum along this axis, that is represented by, sorry, this is final, not this is initial, final vector, this is the final vector. If we slap this vector along this axis, so this is the direction of x component of this vector given by mv cos theta. Okay, and before componenting anything, we must always add the signs. So I assume upwards to be positive, rightwards to be positive, down to be negative, and left to be negative. Okay, now it's clear. So pfi, or x component of final momentum, plus y component of final momentum. Pf is final momentum is divided into x component of final momentum plus y component of final momentum. Any vector, any 2D vector, okay, 3D has little bit of more, curriculum. Any 2D vector, if you divide them into perpendicular axis, if you component them into perpendicular axis, the vector disappears. That means you can always break the vector into two components. Okay, so P final is given as component of final momentum in x-axis plus component of final momentum in y-axis, minus P initial can be given as component of initial momentum in x-axis, this I is for initial, plus component of initial momentum in y-axis. Now look at this diagram. This final component of final momentum in y-axis is nothing but mv sine 60 in downward direction, and component of this momentum or initial momentum is also mv sine 60 in downward direction. So can I say final momentum in y-axis gets cancelled by initial momentum in y-axis because they are the same. Okay, so dp is equals to, now change in momentum is nothing but final momentum in x-axis minus initial momentum in x-axis, because the momentum in y-axis gets cancelled, because the ball does not push the ball upwards or downwards, it only pushes the ball sideways. Okay, so what is pfi, or final momentum, component of final momentum in x-axis, is nothing but minus mv cos 60. Similarly, the component of initial momentum in x-axis is mv cos 60 plus mv cos 60. Okay, this minus came from the formula. Okay, the component of initial momentum in x-axis is positive, because see, if we slap this vector in the x-axis, mv cos 60. Okay, so our dp becomes, a change in momentum becomes minus 2mv cos 60, or 2mv cos 60 is nothing but 2mv cos 60 is 1 by 2, or 2 gets cancelled, or change in momentum becomes minus of mv, or they're asking the magnitude, or our correct option is A. So see, this is the more common method in which we will be dealing with vectors in your curriculum. Okay, now let's do the next question. A 0.5 kg ball moving with a speed of 12 meter per second strikes a hard wall at an angle 30 degree. Okay, with the wall, it is reflected with the same speed at the same angle. If the ball is in contact with the wall with 0.25 second, the average force acting on the wall is. So in motion in a straight line video, I taught you, whenever they are asking average of anything, suppose a force time graph was given, and they are asking you to find the average value of force from time is equals to t is equals to 5 to t is equals to 0. Okay, average is nothing, average of any graph is nothing but area under the graph given by f dt, okay, by range or t final minus t initial, that is determined by, sorry, this was not 0, this was 5, t is equals to 5, okay, time at 5 minus time at 0. Okay, this is the average. This is the formula that you have to apply whenever the average comes up. Average of any graph is given by this formula. Okay, now they are asking the average force. Average force is nothing but f dt. Okay, suppose the ball out here contacted this wall and bounced back for a very small time. The ball contacted on this wall and bounced back for a very small time. The wall applied some force on the ball. Okay, and the question is asking find that average force. So average force is nothing but f dt. Okay, and we know from the formula of impulse, f dt can also be written as dp. So can we replace the f dt by dp out here? Okay, so average force is nothing but dp by dt, or p final. dp is nothing but large change, a change in momentum, minus p initial by delta t, or time final minus time initial. Okay, now what is final momentum? Final momentum, when you break it into component, okay, the ball is going out here and coming out here. The final momentum is minus mv sine 30 I. Why? Because you are slapping this vector in this axis, x axis. Okay, so when you slap this vector in this axis, it becomes minus mv cos 60, and cos 60 and sin 30 is the same thing. Okay, cos 60 is equals to sin 90 minus 30, sorry, cos 60 is equals to cos 90 minus 30, which is equals to sin 30. Okay, so whenever you slap the vector to any axis, that becomes, slapping is cos. Okay, you always slap a cos. I don't know what kind of mnemonics are those, but whatever helps you remember. Okay, wherever you slap something, that is cos, plus cos 60, mv sin 30 plus mv cos 60, mv sin 30 I, okay, plus mv cos 60 j, no, sorry, cos 30 j. Okay, you are slapping the vector, you are slapping the final vector in this axis, so cos 30 j. Okay, initial momentum similarly becomes mv sin 30 I plus mv cos 30 j. Okay, I am assuming this side to be plus, this side to be minus, upward to be plus, and downward to be minus. Okay, so change in momentum is nothing but final momentum minus initial momentum. So when you subtract pi from pf, this component gets cut. See, mv cos 30 j and mv cos 30 j gets cut. So our final momentum minus initial momentum is nothing but minus mv sin 30 I minus of mv sin 30 I, which becomes minus 2 mv sin 30 I. Minus 2 mv sin 30 I. Okay, sin 30 is nothing but 1 by 2, or dp is nothing but minus 2 mv sin 30 is 1 by 2, and the change in momentum takes place in I component or I direction, x axis. Okay, so these two gets cut, or dp is equals to minus mv. I'm not writing I because it is understood that the change in momentum takes place in this direction. So let's find out the value of m. M is given as 0.5 kg. Okay, v is given as 12 meter per second. 0.5 kg and 12 meter per second. Okay. Now, what was the average force? The formula for average force was dp by dt. We are derived from out here. So dp is nothing but minus of mv. Minus of mv is 0.5 into 12 by dt, delta t. Delta t is nothing but the time for which the force was applied, the time for which the wall applied the force on the ball. Okay, it is equals to 0.25 second. Okay, or 0.25 second. 0.25 second. The answer comes out to be 24. Okay, answer is B. There might be some confusion, sir, but the ball is applying some force on the wall. Why are you saying the wall is applying some force on the ball? In Newton's law of motion, whenever you are dealing with a body, okay, see, when the ball is applying, when the ball is coming to the wall, it is applying the force on the wall, it's okay. But in Newton's law of motion, whenever you are dealing with the ball, or whenever you are dealing with the body, you always consider all the forces acting on the body. You are not interested in what this body is doing, okay, or how much force this body is exerting somewhere. You are only interested in how much force is received by this body. So the force, this ball applied on the wall, is equal to the same force this wall applied on the ball. Newton's third law of motion. So we are not interested in who applied whom force. Okay, we are just interested in the magnitude of that force. So we'll continue. So now let's move on to the next question. A player takes 0.1 second in catching a ball of mass 150 gram moving with velocity of 20 meter per second. The force imparted by the ball on the hands of the player is. So this question is saying nothing but a ball is coming with 20 meter per second and a player, this is the hand of the player, okay, he catches it in 0.1 second. Okay, the player catches the ball in 0.1 second. Okay, so what is the force imparted by the ball on the hands of the player? So we know that from Newton's second law, force is nothing but dp by dt. Okay, so initial momentum is nothing but product of mass and velocity. So initial momentum is mass is given as 150 gram or 0.15 kg into velocity into 20, or is equals to 3. Now after the ball is caught in his hand, after the player catches the ball, okay, what is the velocity of the ball? The velocity of the ball is 0. Therefore the momentum of the ball is 0. So final momentum of the ball is 0, because 0.15 into final velocity, which is equals to 0, is equals to 0. So F, or force imparted by the ball on the hands of the player, is nothing but dp. Dp is nothing but change of momentum, or P final minus P initial by dt, or time taken to catch the ball. P final is 0, minus P initial is 3. Okay, out here don't worry about the sign. See, all the options are given in positive. That means they are just asking us the magnitude of the force. By dt is given as 0.1 seconds, or 0.3 divided by 0.1. Sorry, 3 divided by 0.1. Initial momentum was not 0.3. Initial momentum was 3. Okay, so 3 divided by 0.1, our force comes out to be 30 Newton. So option number C is the correct option. So let's check the next question. A ball of mass 3 kg moving with a speed of 100 meter per second strikes the wall at angle 60 as shown in figure. The ball rebounds at the same speed, remains constant. The ball rebounds at the same speed and remains in contact with the wall for 0.2 seconds. The force exerted by the wall on the ball, okay, the force exerted by the wall on the ball is equals to force exerted by the ball on the wall. Okay, we'll learn this in few slides later. That is called third law of motion. Okay, so the arrow of this question was a little bit wrong, so just change the arrow to this direction, or you can do downward direction also. The answer will come out to be same. Okay, so what is asking? The force exerted by the ball on the wall is, okay, so we know that F is equals to dp by dt. Okay, dt is given as 0.1 second, sorry 0.2 second. dt is given as 0.2 second. Okay, dp is nothing but final momentum minus initial momentum. All these are vector units. Okay, final momentum and force are vector units. Okay, time is scalar units, mass is scalar units. Always remember the difference between vector and scalar. Okay, now what is final momentum? Final momentum is nothing but minus mv sine 60 minus mv sine 60 I plus mv cos 60 j plus mv cos 60 j. See, this is the final vector. If we slap this vector to this wall, we get mv cos 60 j, and on the opposite wall we get sin 60 I. Suppose that means I automatically assumed this side to be plus, this side to be minus. Okay, and upward to be plus, downward to be minus. Okay, now what is initial momentum? Initial momentum is nothing but mv sin 60 I plus mv cos 60 j plus mv cos 60 j. Now see this y component of momentum, it is easily being get cancelled. Final momentum minus initial momentum, the y component of momentum gets cancelled. Okay, so what is therefore final momentum minus initial momentum is equals to minus mv sin 60 I into 2 minus of mv sin 60 I, so it becomes minus 2 mv sin 60 I, minus 2 mv sin 60 I. If we minus mv sin 60 I minus of mv sin 60 I becomes minus 2 mv sin 60 I. Okay, so final momentum minus initial momentum is equals to minus 2 mv sin 60 I. Okay, so let's simplify this, or minus 2, what is m? M is given as 3 kg. Okay, v is given as 100 meter per second. Sin 60 is nothing but root 3 by 2, and I cap. Now this 2 and this 2 gets cancelled. Okay, or p final minus initial, or final momentum minus initial momentum is equals to 300 root 3. 300 root 3. Okay, now they are asking the force. So force is equals to dp by dt, or final momentum minus initial momentum, which is equals to 300 root 3 by dt. dt is given as 0.2. Or if we simplify this, our questions comes out to be 1500 root 3. our answer comes out to be 1500 to 3. I expect you all to perform this calculation by yourself. Okay, into 10 into 10, denominator into 10, numerator into 10, 2 and 300 gets cancelled by 150. 150 into 10 is 1500 and root 3 remains as it is. So our correct option is option A. Okay. Now let's read the next question. A ball of mass 150 gram is moving with an acceleration of 20 meter per second, is hit by a force which acts on it for 0.1 second. The impulsive force is, so what is happening out here? Thing that is happening out here is a ball. Okay, someone is applying a force and this force causes an acceleration of 20 meter per second square. Now what happens is, while moving with 20 meter per second square acceleration, there is a stationary object out here. It hits this ball moving with 20 meter per second acceleration, hits this object and this object flies away. So the time of contact for which this ball hits this object is 0.1 second. Because after contact of 0.1 second, this object flies away. Find the impulsive force exerted by this ball on this object. Okay, so we know that. So before writing impulsive force, write down a note. Impulsive force is also called impulse. That means impulsive force is also called impulse. Okay, so from Newton's second law of motion, we did F dot dt, which is the impulse, calculated by change in momentum, is equals to impulse. Or impulse can be also called as impulsive force. Okay, or short-term force. Now from Newton's second law, we know that force is equals to mass into acceleration. The force exerted by this ball would be the force exerted by this ball on this object is equals to the force received by this ball, because the ball cannot generate a force on its own. No? The ball is a dead object, non-living, and without an engine. Okay, so this force is nothing but mass into acceleration, or mass of this ball into acceleration of this ball. So mass of this ball is given as 150 gram or 0.15 kg. Acceleration of this ball is given as 20 meter per second square. The time period for which it hit was 0.1 second. So when you substitute all the parameter in the equation, 0.15 into 20 into 0.1 is equals to dp is equals to impulsive force. So when you multiply 0.15 into 20 into 0.1, we get the option 0.3. Okay, we get the option 0.3. Okay, a particle. So let's read the next question. A particle of mass m is moving with uniform velocity v1. It is given an impulse such that its velocity becomes v2. The impulse is equals to, this is a simple question, impulse is nothing but f dt, which is found out by the formula dp. dp is nothing but final momentum minus initial momentum. Okay, dp is nothing but final momentum minus initial momentum. Final momentum is mv2, initial momentum is mv1. So f dt or impulse is equals to f dt is equals to dp is equals to mv2 minus mv1. We take the m common, m into v2 minus v1. Option number D. Okay. Option number D. Now let's do some revision. Okay. We know that F is equals to dp by dt. Okay. F, Newton said that F is directly proportional to dp by dt. experimentally find out that F is equals to dp by dt. So dp is nothing but dmv, because p is equals to mv. P means momentum is equals to mass into velocity. When you use mathematics to break this up, it becomes m dv by dt plus v dm by dt. In most cases, the mass remains constant. That means this term becomes 0, or F is equals to m dv by dt. In kinematics, we learned dv by dt is nothing but acceleration. So force is equals to mass into acceleration. Okay, force is equals to mass into acceleration. So out here, when mass do not change. Okay. So let's do a question. A body under the action of a force, 6I minus 8j plus 10k acquires an acceleration of 1 meter per second square. The mass of the body is. So I told you how to obtain the magnitude of a two-dimensional vector. So similarly, the magnitude of a three-dimensional vector can be obtained in the same way. 6 square plus of minus 8 square plus of 10 square. So you might have a question, sir, what happens when the three axes, x axis, y axis and z axis, are not 90 degree to each other? That means three vectors are in 3D but not 90 degree to each other. That one come in your NEET curriculum. That one be coming. Okay. So whenever three vectors, you are supposed to add three vectors, they will always be perpendicular to each other. Okay. And the magnitude of the three vectors comes as 6 square, means magnitude of x, the vector on x axis square, plus the magnitude of the vector on y axis square, plus the magnitude of vector on z axis square. Or 6 square plus 8 square plus 10 square. Our thing comes to 6 square is 36, 8 square is 64 and 10 square is 100. So 64 plus 36 is nothing but 100 plus 100 is equals to square root of 200. Okay. So square root of 200 is nothing but 10 root 2. How? 100 into 2, square root of 100 is 10. So now we simply apply Newton's second law of motion, or simplified Newton's second law of motion. We know that force is equals to mass into acceleration. Force we obtained as 10 root 2. Mass, they have asked us in the question. Acceleration, it is given as 1 meter per second. So can I say, by substituting all this value into this equation, can I say mass is equals to 10 root 2 kg is equals to mass? Or option number D is the correct option? No. Let's do the next question. The object of mass 3 kg is at rest. If a force 6t square I plus 4tj is applied on the object, then the velocity of the object at t is equals to 3 is. Out here, t, the force is not constant. That means they are component, and whenever 2D component of vectors are given, always divide them into components. So we know that force is equals to mass into acceleration, and acceleration is equals to dv by dt. Therefore force is equals to m dv by dt. I just reversed it. Okay. So if we multiply this dt on the left hand side, what do we get? We get f dt is equals to mdv. Okay. And do not fear integration. Okay. Not fear integration means integration formula you know, just apply it. Okay. So whenever 2D components of vectors are given, 2D components of any vectors are given, just divide them into components. Okay. So x component and y component. Okay. In x component, what happens? See, what is the x component of force? X component of force is given by 6t square. Okay. Therefore, fx dt is equals to m into dvx, or change in velocity in x component, or 6t square into dt is equals to m dv into change in velocity in x component. Okay. From 0 to t is equals to 3. Okay, see 0 because 0 means stopwatch is always started from t is equals to 0. Okay, from 0 to 3, time is equals to 3. And dv, the final velocity you have to find out, the final x component of velocity you have to find out. The initial x component of velocity is nothing but 0. Why? Body is starting from rest. See, at rest. Okay, so 6t is nothing but, so when you solve this, 6t square becomes 6t cube by 3 dt. Achha, I'll solve this in next page. I'll just solve this in next page. So what is the equation? 6t square dt. So 6t square dt into m dvx is equals to m dvx from 0 to final velocity component in x-axis, and from time is equals to 0 to time is equals to 3, or 6t cube by 3 from 0 to 3 is equals to m vx from 0 to final velocity in x component, or we can cut this 3. Okay, so 2 into 3 cube, 3 cube is nothing but 27. So 2 into 27 is 27, 2 is 14, 54. 2 into 27 is 54. Okay, 54. Okay, minus 0 is equals to m vx. Okay, what is the value of m? What is the value of m? The value of mass was 3 kg. The value of mass was 3 kg. So 54 divided by 3 becomes Vx is equals to 54 divided by 3. 3 1s are 3. 3 7 8. 8 is 24. So the x component of velocity is 18 meter per second. The x component of velocity is 18 meter per second I. Okay. So let's check 18, 18, 18, 3. So this is wrong option. Now let's look for y component. In y component, Fy is given as 4t. Okay. Therefore, Fy dt is equals to m Vy, dvy, a change in velocity in y axis. M dvy, change in velocity in y axis. So similarly, 4t dt is equals to m dvy. So let's do it in next page. 4t dt is equals to m dvy. Let's apply the limits of integration. 0 to time is equals to 3. 0 to y component of velocity, or 4t square by 2. 0 to 3 is equals to m vy, or y component of velocity from 0 to vy, or this 2 and this 4 gets cancelled by 2, or 2 into t square, t is nothing but 3, or 3 square becomes 9, 2 into 9 is 18, minus if we substitute the 0 in value of t we get 0. Okay, minus 0 is equals to m into vy minus 0. Vy is nothing but vy minus 0. M was nothing but 3. So 3 divided by 6, 18 divided by 3 is equals to 6. 6 is equals to vy. Okay, so our correct option is option number B. 89 plus 6j. Okay, 89 plus 6j. Now let's read the next question. A 10 Newton force is applied on a body, produces an acceleration of 1 meter per second square. The mass of the body is F is equals to ma. Force is given as 10. Mass is given, I don't know. Acceleration is given as 1. So can I say mass is equals to 10? Okay? No. So now we learn something about Newton's third law of motion. Newton's third law of motion. What is Newton's third law of motion? So let's see the definition as given in NCERT. The definition as given in NCERT is, to every action there is always an equal and opposite reaction. To every action there is always an equal and opposite reaction. There is always an equal and opposite reaction. My reaction spelling is wrong, so let's correct it. Reaction. This is given in NCERT. So what do I mean by this line? Most of you know it, but simply, this action and reaction are nothing but forces. Okay, so write down a point. Action force and reaction force acts on different bodies in opposite direction. Okay, action force and reaction force acts on different bodies in opposite direction. Okay. So what do I mean by this? Let's take an example. Suppose there is a block and there is another block kept side by side. These blocks are not attached, okay, but they are kept together. Now suppose I apply some force from the left to block A. Now see this block B. The surface of block A will be pushing block B towards right. Okay? The surface of block A will be pushing block B towards right. Now that force is called normal reaction force. Okay? Or NA. Now Newton's third law of motion says that this force will act equal and opposite in nature. That means if this block A pushes the block B in this surface, the block B pushes back block A with equal amount of force in the opposite direction. This is what was Newton's third law of motion. Okay? Or normal force exerted by B. Newton's third law of motion says that normal force exerted by A on block B, NA, is equals to normal force exerted by B on A is equals to NB. Okay? So let's take another example. Suppose this is block A and this is tied to a spring with block B and this is pulled by force. Okay? Now see, when I pull the block B with some force, this rope also tries to pull this block A. So let's draw block A. Now this block A is pulled by some force exerted by the rope, which is exerted by B on the rope. So Newton's third law of motion says nothing but the force with which the rope pulls block A towards the right is equal to the same force the rope pulls the block B towards the left. Okay? See, this A and B are connected by a rope. Okay? F is applied to B. Now B started moving and this rope is tugging this A. So in applied to move A, this rope must apply some force to A, and that is pulling force. So when this rope is pulling this A, okay, B also gets pulled by this rope. See, B is exerting some pulling force on this rope. Similarly, the same equal and opposite pulling force gets exerted on B by the rope. Okay, this is Newton's second law of motion. Okay, so now you say, sir, what about the F? So the person who is applying this force F also gets pulled back with the same amount of force. Okay, but since we are not interested in the person, therefore we leave that person alone. We leave this F alone. Now let's take the example of a rocket. In rocket, what happens? Suppose take this as well. Now in rocket, gases get ejected from out here with high velocity. Okay, so gases get ejected by a rocket. Force by rocket on exhaust gas. Force on exhaust gas. Exhaust gas by rocket. By rocket. That means this rocket is pushing out this exhaust gas. Okay, that means this rocket is farting out this exhaust gas. Newton's law of motion says nothing but the force with which this exhaust gases is being pushed out is equals to the force exerted by the exhaust gas, exerted by the exhaust gas on the rocket, on the rocket. Okay.